Good morning and welcome to the AMS von Neumann lecture, which is a lecture series dedicated to the mathematical legacy of John von Neumann. It's my great pleasure to introduce Nikhil Srivastava. So he came from India for undergraduate studies in the States at Union College in New York State, where he received his undergrad degree in 2005. He went on to a PhD at Yale in 2010 in computer science. And after postdoctoral years at Microsoft and Princeton, he joined UC Berkeley, where he has been ever since, where he's a professor of mathematics and my colleague at Berkeley. So Nikhil is particularly famous for his 2000 solution, published in 2013, of the Catterson-Singer problem, joined with two collaborators, that long-standing problem in operator algebras. He won many prizes, in particular in 2014. He won the Siam-Polya Prize. He was a speaker at the International Congress. He won the 2021 inaugural Cyprian Foyash Prize for contributions to operator theory, the Held Prize of the National Academy of Sciences, and so on and so forth. So Nikhil is a fantastic researcher, but he's also a fantastic teacher, mentor, and colleague to me at UC Berkeley. So we're in for a treat. He will tell us about 4 ways to diagonalize a matrix.
So thank you, Bern. Thank you, Bern, for that most generous introduction. I have a lot to live up to. And it's a pleasure to give the von Neumann lecture about topics that were close to von Neumann's research, as I will talk about later. So this talk is called 4 Ways to Diagonalize a Matrix. It's based on joint work with Jess Banks, Jorge Garza Vargas, Archit Kulkarni, and Shatagi Mukherjee, who were all students at UC Berkeley at some point. And it's about the computational problem of diagonalizing a matrix, which is something many of us do regularly. So here's an outline of the talk. So I'll start by formalizing this computational problem in a way that we can prove things about. And then, as promised, I will tell you 4 genuinely different ways to diagonalize a matrix, 4 different algorithms, and tell you some theorems about their properties and end with what we don't know. So what is the problem we want to solve? So the problem is diagonalization. So given a square n by n complex matrix A, we want to find an invertible matrix V and a diagonal matrix D so that A is equal to V dV inverse. So of course, here, the columns of V, let's normalize them to unit vectors, are the right eigenvectors of A in such a matrix, and the entries of D are the corresponding eigenvalues of A. Okay, so as stated, this is not really a sensible computational problem for 2 reasons. So the first reason is that if n is bigger than 5, you cannot actually ever solve this problem exactly. You cannot find the eigenvalues and eigenvectors exactly in finite time. And the second problem, so this first issue means you need to settle for some approximate version of the problem. And the second issue is that this is a problem about complex numbers, and if you actually want an algorithm that can run on a computer, you cannot store real or complex numbers exactly. You can only store some kind of approximations of the numbers. So to formalize the problem, we need to handle both of these issues. And so first, I'm going to consider this problem of approximate diagonalization, which formulated as follows. The input is now a square n by n matrix A, as well as a real accuracy parameter epsilon. And the goal is now to find invertible V and diagonal D so that A is close to V dV inverse in this sense. So the operator norm of A minus V dV inverse is bounded by this accuracy parameter epsilon times the operator norm of A. So this is a well-defined computational problem. The input is A and epsilon. The output is V and D with this property. Now, the notion of approximation is something which you may or may not be used to. It's called backward error. This is the standard notion of approximation in numerical analysis. And what this is saying conceptually is that given an input A, what I want to find the exact diagonalization of a nearby matrix A prime, as shown in this picture. So you give me A and epsilon. What the algorithm should do is output some V and D so that A prime equals V dV inverse, where A prime is epsilon close to A in the operator norm. So this is called backward error. This is the standard notion of approximation in numerical analysis, and the approximation happens in the input space in this notion. And this terminology, backward error, is used to distinguish it from another natural notion of approximation, which is forward error, which would be that given an input, I want my algorithm to produce an approximation to the exact output for that input. So these are two different notions of approximation. In this talk, we will be focusing on backward error. Okay, so that's our notion of approximate diagonalization. And now we have to talk about the second issue. Well, our algorithm is going to do some kind of arithmetic operations to solve this problem, but we can't do real number arithmetic on a computer. And so the model we'll consider is called floating point arithmetic. So this is a realistic model of computation that's actually implemented on computers. It's a noisy model of arithmetic. And roughly speaking, what the model is that you can do all arithmetic operations, addition, multiplication, subtraction, division, up to a multiplicative error of 1 plus or minus 2 to the minus b, where b is a parameter called the bits of precision. So the more precision you have, the more accurately you can do arithmetic. And precision is viewed as a resource. The more precision you have, the more time it will take on your computer. So this is a formal computational model. And now we have a well-defined mathematical problem. The question is, can we design a provably efficient algorithm for this approximate diagonalization problem, which works for every input? So that means for every a and epsilon, it performs some sequence of floating point arithmetic operations to produce a v and d that satisfy this backward error guarantee. And efficiency will be measured by two functions. So one is the number of arithmetic operations. I'm going to call that T of n and epsilon. So it should only depend on the size of the matrix and on the desired accuracy. And the other important parameter is this number of bits of precision, this function b of n and epsilon. So I want an algorithm which always produces an approximate diagonalization using at most t arithmetic operations with b bits of precision. And I want this to be small. That's what efficiency means. So that's the statement of the problem I want to study, design of algorithms with this property. OK. Now, before I dive into the algorithms, there are two important distinctions in this area. So one is between theory and practice. So many of us probably solve eigenvalue problems every day on our computer. And I should say that in practice, this is considered a solved problem in the sense that there is very good software, like MATLAB, LAPACK, et cetera, which almost always works. OK, so how many people have ever seen a matrix on which MATLAB fails? Yeah, no one. You're not going to find it unless you're really looking for it. But these matrices do exist. So at present, there's no software that provably actually solves this problem for every input. And the reason for that is that all of the known software is based on heuristic algorithms that do not have proofs of correctness or efficiency. So either the algorithm can be very slow, or it just may not converge. OK, so the goal of this talk is not to improve this existing excellent software that exists for this problem. The goal is to design algorithms that are provably always correct and efficient. So that's a theoretical study of this problem. The second important distinction is that there's a big difference in this problem between normal matrices and non-normal matrices. Okay, so a normal matrix is a matrix which has an orthogonal basis of eigenvectors. And if you restrict attention to normal matrices, then this problem is solved both in theory and in practice. So there's a famous result of Wilkinson from the 1960s, which shows that if the input matrix A is normal, then this approximate diagonalization problem can be solved using n cubed log n over epsilon arithmetic operations with log n over epsilon bits of precision. So importantly, this bits of precision is a very slowly growing function of the input size and the precision. And this matches the observed practice as well. So for normal matrices, theory and practice are very close. The challenge is to prove similar bounds for non-normal matrices. Now, why is there such a difference between normal and non-normal matrices? So let me show you two examples. So here's a normal matrix. It's actually a symmetric matrix. Its spectrum is very simple. There's these real numbers, cosines. And this picture is its orthonormal basis of eigenvectors. So a normal matrix has the property that if you perturb it a little bit, let's say you perturb it by some matrix E of norm epsilon, then the spectrum also only gets perturbed by epsilon. So spectrum of normal matrix is stable. On the other hand, here's a non-normal matrix A, which actually has the same spectrum. It's actually similar to the first matrix. However, its eigenvectors are highly non-orthogonal, as indicated in that cartoon over there. So it has the same spectrum. But now, if you perturb this matrix A, this non-normal matrix A, by a matrix of size epsilon, you can see that the spectrum can change by at most 2 to the n times epsilon. So this is the key phenomenon that makes the non-normal case difficult, spectral instability. Spectra of non-normal matrices can be highly unstable under perturbations. And so, in this example, for example, if you add a perturbation of size 10 to the minus 10, then this is what happens to the spectrum. You get a huge change in the eigenvalues that you can see on this macroscopic plot. This is the essential difficulty, that we want to have algorithms that we can prove things about, and we want to use a small amount of bits of precision, so we want to allow noisy arithmetic. But how can we possibly prove something if the quantities considered by the algorithm are so unstable? That's the essential difficulty in this problem. OK, so that's the setup. Let me now tell you the 4 different algorithms. So the first algorithm is based on the characteristic polynomial. It's based on, I suppose, high school algebra. It's not really algebra. It's the algorithm that we all know and learn in undergrad or whenever. So the idea is very simple. If you have a square matrix A, then its eigenvalues are equal to the roots of its characteristic polynomial, which is this univariate polynomial determinant of z times identity minus A. And so the idea is, well, why don't we just compute the characteristic polynomial and then find the roots of the characteristic polynomial? Now, of course, that's a non-trivial problem. But finding roots of polynomials is a highly developed area. And so there are algorithms for doing that. And so why not just do that? So the key result that this approach rests on is something I'll call theorem R, which is due to Smale and Schoenhager in its initial form and due to Pan in its final form, which is a theorem that says you can find roots of polynomials efficiently. And here's what it says. If you have a rational polynomial P with roots in the unit disk, then there's some algorithm that finds epsilon approximations of all the roots in order n squared plus log 1 over epsilon bit operations. OK, so this is a heavy theorem. This is a long line of work, but this is the end result. So if you have theorem R in hand, then there's a very simple algorithm for finding eigenvalues of matrix. Step 1 is you compute the characteristic polynomial. And step 2 is you use theorem R to find some epsilon approximations of the eigenvalues. OK, so let's see how this does. So I went on MATLAB. I generated a random plus minus 1 matrix of size 100. You can see using random matrix theory that its eigenvalues lie in this interval minus 20 to 20. And I computed the characteristic polynomial, and that's what it is. OK? So this took about 4 minutes to compute on my laptop for a 100 by 100 matrix. And the key feature here is that the coefficients are huge. They have many digits. And in general, if you compute the characteristic polynomial of an n by n matrix, the coefficients will grow exponentially in n, and you will need about n bits of precision to even write down the characteristic polynomial. So that's observation 1. The coefficients of the characteristic polynomial are huge. Observation 2, which is famously due to Wilkinson in the 1960s, but has probably been known for a long time, is that the roots of a polynomial are extremely sensitive to perturbations of the coefficients. So here's a famous example. It's a polynomial of degree 20 with integer roots 1 through 20. And this could arise as the characteristic polynomial of a diagonal matrix, even, of a very nice diagonal matrix. But if you now perturb this by one of the coefficients by 2 to the minus 30, you get some macroscopic changes in the eigenvalues. So this plot, the green circles are the eigenvalue, are the roots of this polynomial W that's shown here, and these black dots are roots of random perturbations of that size, of that polynomial. And so observation 2 is that the roots are highly sensitive to changes in the coefficients, and even exponentially small changes in the coefficients can change the roots macroscopically. And so the combined effect of these two observations is that the characteristic polynomial is an extremely brittle way of computing the eigenvalues of a matrix. And in order to make this work, you need to do all of your computations to about order n bits of precision, because you need exponentially good, exponentially small noise in your arithmetic operations. And so what this is saying is, if you do this, you need to use a lot of precision. And indeed, this is sufficient. So there's a theorem, due to Pan and Chen from '99, which says that this algorithm works. It actually yields forward error, that distinction is not so important for now. It works. It requires n to the omega plus n log 1 over epsilon arithmetic operations. So this number omega is the exponent of matrix multiplication. And we don't know what it is. It's somewhere between 2 and 3, and right now an upper bound is 2.37. So the number of arithmetic operations is about the time it takes to multiply matrices. But the issue here is that the bits of precision needed is n plus log 1 over epsilon. So it grows linearly in the size of the matrix. And the end result is that this algorithm is very slow, and you can't really use it for large matrices. So yeah, so what's good about this algorithm is it is useful because it gives you forward error. In some kinds of applications, if you're doing representation theory or something like that, then you need forward error. And this type of algorithm is useful, and it is used. The downside is it's just too slow for any large matrices because of this n bits of precision. So that's algorithm A. So I'm going to just record the different algorithms in this table with their key properties. So algorithm A is this characteristic polynomial algorithm. The runtime is roughly matrix multiplication arithmetic operations, but the precision is high. So I'm going to refer to this as a high precision algorithm because it uses n bits of precision, but also a high accuracy algorithm because the dependence on epsilon is logarithmic. So I can set the accuracy epsilon to be very small and not blow up the time. So it's a high precision, high accuracy algorithm. Okay, so that's not very satisfactory, and for a long time that was the only provable algorithm that you could prove anything about for computing eigenvalues of general matrices. And there was a question in numerical analysis that was mentioned by many different people, but in particular by Jim Demel in 1997, which is there any algorithm for this problem that uses uses a logarithmic amount of precision, uses order log n over epsilon bits of precision? So this is, in numerical analysis, this is called numerical stability. And this log n over epsilon precision, this is, remember, this is how much the algorithm for the normal matrices required. So the question is, can we get the same thing for non-normal matrices, for general matrices? So, so this question, yes, was open for a while, and some significant progress on it was made in 2015, and now I'll tell you about the second algorithm which made that progress. So this is based on an essentially geometric idea called homotopic continuation. And what's the idea? So this is an idea which originated in the work of Lahai in 1934 and was popularized by Smale and Shub and others in the 1980s. And the idea is very natural. The idea is, suppose I want to find the approximate diagonalization of a matrix A. Well, that might not be so easy. So maybe what I can do is find some other matrix, A naught, for which it's easy to solve the problem, let's say a diagonal matrix. And then I can slowly deform A naught into A via some kind of homotopy. Let's just say linear homotopy for now. So I define this function A sub t, which is just 1 minus t times A naught, my easy matrix, plus t times A1, which is my actual matrix I care about. And then, maybe I can slowly deform this matrix and keep track of the solution in some way so that in the end I get the solution to the problem I wanted. So that's the high-level idea. Now, what is the mathematical instantiation of this idea? Well, for this problem, we define a set called the solution variety, which is the set of triples of matrices A, D, and V, where A is any matrix, D is diagonal, and V is an invertible matrix, such that A is equal to V dV inverse. and V is normalized to have unit norm columns. So this is the set of all triples such that A is equal to VDV inverse. So and it's a variety because it's defined by some polynomial equations. So let's call this M. Now, inside this solution variety M, there is a particular subset that's kind of problematic. This is going to be, this is the set B, which is the set of triples A, dV, such that A has a double eigenvalue. And the reason this is problematic is that the diagonalization problem is not well posed at points in this ill-posed variety B. So in particular, the eigenvalues are not unique, and if you have a smooth parameterization of if you have a curve inside the set, it won't be the eigenvectors won't be differentiable functions of the matrix. Okay, so you have the solution variety M, and you have this ill-posed variety B, and an easy to check fact is that the map from T, the homotopy parameter, to the triple of matrices A sub T, D sub T, V sub T, this is smooth on the complement of this ill-posed variety. So this is just a fancy way of saying that if you have a matrix with distinct eigenvalues, then the eigenvalues and eigenvectors are differentiable functions of the matrix. Okay, so this is the setup. And now, if you want to execute this idea, the challenge is you want to find a path between 2 points in the solution variety. So the first is the matrix you care about, A1, D1, V1. You don't know what D1 and V1 are. And the second is the matrix that you start off with, the easy matrix. So that's A0, D0, V0. You want to find a path that avoids this ill-posed variety, and you want to find some way to efficiently compute points on it. You want to slowly update the solution as you walk along this path. So that's the high-level idea. And I would say that the key development in turning this idea into algorithms in the 1980s, due to Smale and Renegar, improved by Renegar, is the following theorem. And what it says is, if you have a point on the solution variety whose distance to the ill-posed variety is large, so it's bounded by some number square root h, then there's an efficient way to increase the homotopy parameter by h. So all this is saying is that if you're far away from the ill-posed variety, you can efficiently move along this homotopy path using Newton's method, which is some standard optimization method. And what this says is the farther you are from the ill-posed variety, the faster you can move along this path. And the beauty of this theorem is it reduces the computational problem to a purely geometric problem. So what it says is if you can find a path that avoids this set B, then you get an efficient algorithm. And so now this reduces our problem to this new challenge prime, which is simply how do you find a path in this space that avoids the set B? Okay. Now, the reason this is tricky is that you don't know the eigenvalues of your matrix A1 that you care about, right? And so how are you going to find a path from A0 to A1 that avoids B if you don't even know what this looks like inside the solution variety? Okay, so the important progress that was made in 2015 due to Armentano, Beltran, Bergesser, Cooker, and Chubb is the following theorem. So the theorem introduces randomness into this problem, and here's what it says. It says if you have any pair of matrices A0 and A1, let's consider a Gaussian random matrix G. So that's a square matrix whose entries are IID complex Gaussians. And let's consider the homotopy between A0 and A1 plus epsilon G. So we randomly perturb one of the endpoints of the homotopy. So this gives us now a random path in this space. Then, with high probability, this path is well separated from the ill-posed variety. So this is a probabilistic result, saying if you perturb one of the endpoints, then with high probability, the whole path is well separated from this bad set. And the bigger you make the perturbation, the more separated you are. That's what this is saying. And the proof is a kind of very geometric probability, integrable probability kind of proof. It's based on things like the change of variables formula for Gaussian integrals on manifolds and things like that. And you can the proof computes everything very exactly. So it's a very clean proof. OK, so what's the upshot of this? Well, the upshot of this is that if you want to now find an approximate diagonalization of a matrix A, well, because you're allowing epsilon backward error, it's OK to compute the approximate diagonalization of A plus epsilon G, where G is, let's say, a Gaussian random matrix of norm 1. And so what this is saying is that if I'm OK with backward error epsilon, I can do this for free. I can add a Gaussian perturbation to the input, and I still have a small backward error. And this idea is inspired by, I would say, the works of Spielman and Teng, and also an important paper of Brian Davies about approximate diagonalization from 2006. So given this theorem, there's a very natural algorithm, which I'm going to call algorithm H, which has 4 steps. The first step is you choose some matrix for which this problem is easy to solve and away from this ill-posed variety. For example, just take A naught to be a diagonal matrix with some well-spaced eigenvalues. The second step is you add a random Gaussian matrix G, epsilon times a Gaussian matrix G, to your matrix A that you actually care about, and you consider this random homotopy A sub T. Then, by the theorem, this whole path is well separated from this ill-posed variety. And so, by Smale's theorem, you can take large Newton steps along this path efficiently. So in particular, you can set the step size to be this quantity epsilon squared over n to the 4th. And then you just repeat this to go from the beginning of the path to the end of the path. That's algorithm H. So let me show you a demo of what this actually looks like. OK. So what I'm plotting here is the eigenvalues of my matrix as I walk along my homotopy path. So right now, I'm at A naught. So this is just a diagonal matrix whose eigenvalues are grid points in this square. And now I'm going to start evolving time. So you see this parameter t is going up. And what I'm plotting is just the eigenvalues of the matrix that appears at time t. And what's happening is that, well, indeed, the eigenvalues are moving around because the matrix is changing. And I'm slowly deforming the eigenvalues of this easy matrix at time 0 into eventually what will be the eigenvalues of the matrix that I care about at time 1. And the actual algorithm will also keep track of the eigenvectors while doing this. So the important thing to note is that as these eigenvalues are moving around, they don't touch each other. So touching each other is what it means to be in this ill-posed variety, and that doesn't happen. And the random matrix theory result says that it will not happen. So that's how homotopy continuation works. OK, so when the dust settles, they were able to prove this theorem, which says that algorithm H provably correctly solves the approximate diagonalization problem in n to the 10 over epsilon squared arithmetic operations using order log n over epsilon bits of precision. OK. Now, what's good about this is that this is the first provable algorithm for general matrices for solving this problem that uses order anything close to logarithmic bits of precision. In fact, it uses the optimal amount of precision. So it uses a very small amount of precision. It's a very robust algorithm. The bad thing about this algorithm is that, of course, the running time is very large. Both the dependence on epsilon is very bad. It's 1 over epsilon squared. It's not log. It's polynomial in 1 over epsilon. And the dependence on n is also very large. So this is not actually an algorithm that you would use in practice because it's very slow, even though the precision is very low. And one remark I want to make is that the reason it's slow is that this algorithm is an extremely general algorithm that can be used to solve all kinds of other things like systems of polynomial equations, et cetera. And so it's really not exploiting the structure of the eigenvalue problem very much, and I would say that's why it's slow. Okay, so that's the second algorithm, homotopic continuation. And this algorithm, it uses low precision, which is good, but it also has low accuracy. You cannot set epsilon to be very small because the dependence on epsilon is polynomial. So this question remains, is there an efficient high accuracy algorithm which uses low precision? Okay, so let me now get to the third algorithm, which makes progress towards this question. And this is essentially based on ideas from, I'd say, complex analysis, function theory, approximation theory kind of ideas. So the key player in this algorithm is something called the sign function of a matrix. So let me first define the sign function of a number. So if you have a complex number z, which is not on the imaginary axis, then the sign of z is just the sign of the real part of z. So it's +1 in the right half plane, -1 in the left half plane. That's the sign function of a number. The sign function of a matrix, I'm just going to define, so if I have a diagonalizable matrix A with eigenvalues eigenvalues d, I'm just going to define the sign function of the matrix to be the matrix with the same eigenvectors, but I replace the eigenvalues by their signs. So what happens is shown in this picture here. On top, I have the spectrum of some 7x7 matrix in the complex plane. When I apply the sign function, it should just map all of the right half plane eigenvalues to 1 and all the left half plane eigenvalues to -1. Okay, so what's the upshot of this sign function? Well, the nice thing about it is if I have the sign function of a matrix, then I can easily compute spectral projectors onto the eigenspaces corresponding to eigenvalues in the right half plane and the left half plane, if I just average this matrix with the identity. So I can compute the sign function, I can compute spectral projectors onto subsets of the eigenvalues given by the right and left half plane. And there's this very nice idea of Beavers and Denman from 1974 in the numerical analysis community. And what they observed is that if the eigenvalues are spread out, are well spaced in some nice sense, which I won't make rigorous, then if you can compute the sign function, you can do a kind of divide and conquer algorithm. You can split the eigenvalues in half, and you can somehow restrict attention to a matrix with half as many eigenvalues, and you can do recursion. And it was proven by Demel, Dumitru, and Holtz in 2007 that actually if you can compute the sign function of a matrix, then you can efficiently approximately diagonalize a matrix using this kind of recursion idea where you project onto half the eigenvalues. And so for the rest of this section, I'm just going to talk about how to compute the sign function of a matrix efficiently, because that's enough to solve the approximate diagonalization problem by this work of Demel, Dumitru, and Holtz. Okay, so how do you compute the sign function of a matrix without knowing the eigenvalues? That's the question. Well, let's start with how do you compute the sign function of a number. So suppose I want to compute the sign function of a complex number z. Here's a way to do it that goes back to Zolotarev in the 1800s. I'm going to define the rational function g of z, which is just z plus z inverse divided by 2. And I'll notice that this rational function has two fixed points, +1 and -1. And so the important property of this function is that if you iterate this function, then actually any complex number that's not on the imaginary axis will converge to one of these fixed points. And to see this, we need to consider a certain set in the complex plane. So we have this function g of z. Now I'm going to define a family of circles, C plus sub alpha, indexed by a positive parameter alpha that's less than 1. And C plus sub alpha is the set of points in the complex plane such that the distance to 1 divided by the distance to -1 is at most alpha. So the ratio of distances to these 2 points is at most alpha. Now it's a classical fact that goes back thousands of years that this set is a circle. It's called a circle of Apollonius. So I have this family of circles in the right half plane. Similarly, if I consider the inverse ratio, then I have a family of circles in the left half plane, which I will call C sub alpha, C minus sub alpha. So I have these families of circles, circles of Apollonius. And a very simple fact, which has a two-line proof, is that this function g maps C alpha to C alpha squared, either in the right or left half plane. So it's very strongly contractive towards these points +1 and -1. And so once you have this, you have an algorithm for approximately computing the sign function of a number, which is very simple. You start with the number that you care about, assuming it's not on the imaginary axis, and you just keep applying this function z. You just keep averaging it with its inverse. And according to this, by this key fact, the kth iterate of this process will lie in a circle of Apollonius whose circle parameter is alpha naught to the 2 to the k, if the initial circle that the point was in had a parameter of alpha naught. So, and of course, as alpha gets smaller, these circles are getting smaller and smaller. So in particular, if you want to compute the sign function of a number to error epsilon, and you then what you can do is you can iterate this log 1 over 1 minus alpha naught, where alpha naught is the circle parameter of your initial point, plus log 1 over epsilon times. And because the circle parameter is getting squared every time, you get this quadratic convergence. So that's how you compute the sign function of a number. Now, a very nice observation due to Roberts, who was a numerical analyst in 1972, is that the same algorithm works for matrices, just by the spectral mapping theorem. So now I'm going to define a function on matrices. G of A is just A plus A inverse divided by 2. And the spectral mapping theorem says that the spectrum of G of A is equal to G of the spectrum of A as long as G is analytic in a neighborhood of the spectrum of A. So in particular, if you have a matrix which has a spectrum that's disjoint from the imaginary axis, then the same algorithm works and the same proof works. So if you just, the algorithm now is you just take the matrix and average it with its inverse and keep doing that. By the spectral mapping theorem, the spectrum of the kth iterate is contained in the circle with parameter alpha naught to the 2k. And again, by the same kind of reasoning, you get that the spectral radius of the kth iterate converges, minus the sign function converges at this log 1 over epsilon rate, just as we wanted. So this is a very simple algorithm. It's a two-line algorithm. Just keep applying this function to compute the sign function. So what does this look like? Let me do a little demo. So this is me running the sign function algorithm on the same matrix that I showed you in the previous demo. So this is a plot of the eigenvalues. Oh, wait. Oh, you're not seeing the plot. OK. Yeah. OK, yeah. So this is a plot of the eigenvalues of my initial matrix A, whose sign function I want to compute. This is G to the 0 of A. So this is the spectrum of A. When I apply this function G once, this is what happens to the spectrum. So it looks like it kind of explodes. But I mean, actually, it is contracting if you view it in these circles of Apollonius. And here's what happens if I apply it again. And if I just keep doing this, I mean, unless you know about these circles, it's not obvious that you're making progress. But indeed, after what appears to be 7 iterations, this is pretty close, or I don't know, certainly after 9 iterations, it looks like it's a sign function of a matrix. So that's the sign function. That's the iterative algorithm for computing the sign function of a matrix. And why are we not done? So why is this not just an algorithm that has all of the properties we want? Well, the reason is this proof doesn't work in finite arithmetic. If you're doing things in floating point arithmetic, you don't actually just keep applying this function. You're adding a little bit of noise at each step. And so really what's going on is this noisy iteration where A sub k plus 1 is G of A sub k plus some error ek. And the reason this didn't give a provable algorithm in floating point arithmetic is that there wasn't really a way to analyze convergence with noise. Because now the matrices don't commute. If they're non-normal, then everything is quite unstable. And the challenge was, how do you analyze convergence when you have this noise? So there was a line of work in the numerical analysis community where they showed that if this converges, then it's correct. But this question of actually proving that it converges with this floating point error was open. And so recently, we proved this theorem in 2019, which says that we can prove convergence, we can prove rapid convergence with control on the number of bits of precision if we first add a random Gaussian matrix. So it's the same trick that was used in the previous homotopic continuation algorithm. So the theorem says, given any matrix A and some desired accuracy epsilon, let's say you add epsilon times a complex Gaussian random matrix to A. Then with high probability, this spectral bisection algorithm, that's what this is called, converges in, so it converges, and the number of arithmetic operations it uses is almost matrix multiplication number of operations. So n to the omega times log squared n over epsilon. So that's very low. And it uses log to the 5 n over, sorry, that should be epsilon bits of precision. OK, so that's not log to the 1 n over epsilon, but it's better than n. And the key ingredient in the proof is a random matrix result, which I'll call almost normality result. And this result was conjectured by Brian Davies in 2006. And what this says is that if you take any matrix and you add a small Gaussian random perturbation to it, then with high probability, the eigenvectors of the perturbed matrix will be well-conditioned. So well-conditioned means they kind of look like an orthonormal basis. And so that's shown in this picture here on the right. I can start with a matrix A that has some very skewed eigenvectors. But when I add a Gaussian random perturbation, it will end up being kind of orthogonal in a sense. And of course, how orthogonal depends on epsilon, but I'm not saying that here. The proof uses some results in random matrix theory due to Edelman and a result in free probability due to Schneidi. So that gives us an algorithm for solving the approximate diagonalization problem. Now, the good thing about it is it's fast. The arithmetic operations are n to the omega instead of n to the 10. It's high accuracy. The dependence on epsilon is also mild. But the downside is the precision is still not really practical. Log to the 5 n or epsilon, if you're a theoretical computer scientist, you think that's OK, but it's really not OK. So this is where we are now. We have these 3 algorithms. And this last algorithm that I presented, it does a lot better on the runtime, but it does worse on the precision. It's log to the 5 instead of log to the 1. And so this question is still open. Is there an efficient algorithm which uses log to the 1 n over epsilon bits of precision? And that brings us to our last algorithm, which is called shifted QR, which is the oldest algorithm that I'm going to talk about. And the essential phenomena here are kind of dynamical. OK, so what is the shifted QR algorithm? So it's an algorithm that was discovered in 1961 independently by Francis and Kublanovskaya during the Cold War. And the first idea here is let's not try to compute the eigenvectors of our given matrix. Let's instead try to compute the Schur form. OK, so every matrix is unitarily similar to an upper triangular matrix. That's called the Schur form. And so the shifted QR algorithm is a way to approximately compute the Schur form of a matrix. There is a way to get from that to the eigenvectors that I will not talk about. And the idea, which is very elegant, is to consider the following isospectral iteration on matrices. So that means you don't change the spectrum. Unlike all the previous methods we saw, this method does not change the spectrum of the matrix. So you start with an iterate A naught, which is just your matrix that you care about, A. And then in each iteration, what you do is you take your matrix A sub k, and you compute its QR factorization. So you do Gram-Schmidt. So you write it as unitary times triangular. And that gives you a unitary matrix Q sub k. And now your next iterate is you just conjugate the matrix with that Q. That's it. That's the algorithm. Okay, so in every step, you compute QR and you conjugate with Q. Okay, so it's fairly straightforward to show that if you have a matrix with eigenvalues which have distinct magnitudes, then this actually converges to an upper triangular matrix. Okay, so if you start with a matrix with eigenvalues of distinct magnitude, this procedure will converge to an upper triangular matrix, and then you're done, because then when you multiply together your accumulated Q sub k's, you have found a unitary similarity between your matrix and an upper triangular matrix. The problem is that the rate of convergence depends on the ratio of magnitudes of eigenvalues, which can be arbitrarily slow. So there's no bound on the rate of convergence in general. And this is not just an artifact of the proof. So here's an important example. Let's say my matrix is unitary. So let's say I start with a unitary matrix. So then A sub k is unitary. Well, what's the QR factorization of a unitary matrix? It's just itself, right? So it's already unitary. And so what is the update going to be? Well, the next iterate A sub k plus 1 will just be conjugating A sub k by itself. But that doesn't change A sub k because it's unitary. So actually, unitary matrices are a fixed point of this dynamics. And so this really does not work. This explains why this condition about having eigenvalues of equal magnitude could be a problem. So that doesn't give you an efficient algorithm. And the key idea of Francis and Kuplanovskaya, which is why it's called a shifted QR algorithm, is to introduce one more parameter into this and say, well, at the kth step, instead of just computing the QR factorization of A, I'm going to shift the matrix by some multiple of the identity. So that's going to change the QR factorization in some way. So it gives you a one-parameter family of orthogonal matrices at each time step. And the intuition is that this should speed up the convergence, or at least get you out of the fixed points. And the reason for that is that, going back to our unitary example, I have this bad matrix that's unitary. All the eigenvalues are on the circle. It's a fixed point. Well, if I shift the origin to be some other point, then the eigenvalues are no longer on a circle. So by shifting the matrix, I at least escape these fixed points. That's one intuition for why this is a reasonable idea. So this is called the shifted QR algorithm. And in order to specify it, you need to specify a rule for picking these shifts. And the challenge is, what should be the shifts? Like, you don't know the eigenvalues of the matrix. And so how do you efficiently figure out shifts that will lead to convergence without knowing the eigenvalues of the matrix? So let me just briefly tell you the history of this algorithm. So it was discovered in 1961. So I'm going to call it algorithm Q, and it's defined by a shifting strategy, which is a function from matrices to numbers, which are shifts. So the most important result is the result of Wilkinson from 1968, who showed that if you have a Hermitian matrix, then there is actually, for Hermitian matrices, there is a shifting strategy which always converges rapidly. This is a highly non-obvious shifting strategy. And what this implies is that for Hermitian matrices, you can get a running time where the number of arithmetic operations is roughly n cubed, and the number of bits is log to the 1 n over epsilon. So this is the algorithm I mentioned in the beginning of the paper, beginning of the talk, that works for normal matrices. So I mean, this is for Hermitian matrices, but you can reduce the normal case to the Hermitian case. So for Hermitian matrices, this is very well understood. And the main question about this was, what about non-Hermitian matrices? So this was studied by people in numerical analysis and dynamical systems in the 80s and 90s. And there are many papers written about this. And roughly the picture that emerged is that any shifting strategy you try for non-normal matrices could have some kind of very complicated dynamics. So so in particular, you could have chaotic behavior. You could have periods of arbitrary length. You could have attracting cycles and all kinds of not nice dynamical behavior if you want to prove rapid convergence. So this thing on the right is a picture pulled from one of these papers. I won't describe it precisely, but it's a picture of basins of attraction for this dynamics for a certain shifting strategy that was used called Rayleigh quotient iteration. And you can see that these pictures are pretty complicated. so I would say the one mystery about this was, what does this do on non-normal matrices? And there were other interesting things proven about this. For example, here's a theorem of late Saldana and Tomei, who proved that if you have any shifting strategy that's convergent on every Hermitian matrix, it has to be a discontinuous function of the matrix. Okay, so the last result I want to mention is a recent work of Banks, Garza, Varga, and myself, where we showed that where we found a shifting strategy that provably converges rapidly, not on every matrix, but with high probability on a small random perturbation of every matrix. So the theorem says there is a shifting strategy such that if you, for any matrix A and epsilon, if you look at A plus epsilon G, where G is a complex IID Gaussian matrix, then with high probability, this algorithm Q converges rapidly. And the running time is n cubed log squared n over epsilon, so one extra log factor compared to the Hermitian case. And the number of bits of precision is log squared n over epsilon, so also one extra factor compared to the Hermitian case. So I won't talk in detail about the proof. My collaborator, Jorge Garza Vargas, is giving a 1-hour talk about this at 5 p.m. today if you want to see it. But again, some kind of almost normality theorem from random matrix theory plays a key role in understanding the transient behavior of the dynamics. And there's also some kind of symmetry breaking that's required. So, okay, so what are the pros and cons of this last method? Well, this is close to the algorithm that is actually used in practice. So whenever you compute eigenvalues on your computer, this is what is being done, some version of this algorithm. It uses significantly lower precision than the spectral bisection algorithm. It uses log to the 2 n over epsilon bits of precision instead of log to the 5 n over epsilon bits of precision. But the downside is, I mean, there's still this log to the 2, right? Like, if you really want theory and practice to coincide, this log to the 2 is still not what is actually implemented in software libraries. So this is the current state of the art, that we have these 4 algorithms. The last one is pretty close to what we want. The runtime is low. The dependence on the accuracy is good. The precision is kind of low, log squared n over epsilon, but this question is still open of log to the 1 n over epsilon. And the common ingredient in all of these, in the last 3, which were the real algorithms for this problem, the common ingredient is you had to use a random perturbation. You had to prove some kind of random matrix theory result to control the non-normality of these matrices. So this question is still open. Is there an efficient high accuracy algorithm that uses log to the 1 n over epsilon bits of precision? And I think there are some serious mathematical questions hidden in this. I'm happy to talk more about it later. And there's a there's a special session today about things related to this. So let me end, since it's a von Neumann lecture, let me end by showing you a picture, an excerpt from von Neumann's paper, Numerical Inverting of Matrices of High Order from 1947, published in Bulletin of the AMS. And this paper was a seminal paper both for numerical analysis and random matrix theory. So it's about the question of how do you invert a matrix. And in this paper, they introduced actually a lot of the things we were talking about. They introduced this formal model of round-off errors, which is this floating point, similar to the floating point model of computation. And they even studied what would happen to the conditioning of various of various matrices on taking the matrices to be random. And I mean, as you can see, this randomness ended up being like the key thing in proving anything about all of these algorithms over the last couple of decades. So yeah, I'll just end there.
So there's a distinction between normal and non-normal matrices. Orthogonal matrices are normal, yet they're the fixed point of the QR algorithm. So can you give some insight about how shifting is really critical, given that these are normal matrices? They're supposedly nice, but they're really the enemy of the QR algorithm.
Yeah, so in the QR algorithm, there are actually two enemies. So one enemy is symmetry, as seen in the case of orthogonal matrices, eigenvalues on the circle. And the shifting strategy has to somehow break this symmetry in order to make progress. And that is a completely distinct enemy from non-normality. So non-normality causes some kind of weird, like transient, non-monotone behavior in the dynamics. And this is just a different problem. And so the random perturbation takes care of that problem, and you need some other idea to take care of the symmetry. So they're really two different issues. Yeah.
I hope is a trivial question. In the bisection algorithm, if you're on the imaginary axis, there's a problem.
Yeah,
So what do you
so
do
this
with
is
that?
something I kind of ignored. So indeed, in the bisection algorithm, you better not have eigenvalues near the imaginary axis, or you will be, well, or you'll have slow convergence. So one other ingredient in this theorem that I didn't mention is we proved that for a random perturbation of any matrix, the eigenvalues are well spaced. And that then we choose a random offset, and that allows you to avoid this problem.
I have actually two questions. The first one is really short. The very last slide you showed, excuse me, had a photograph of von Neumann and three other people. Who are the other three people?
So it's von Neumann, Goldstein, and I don't know who the other people are. I should have checked. I think this was taken Oppenheimer. OK, yeah. Oh, yeah, OK. I guess I haven't. Well, one of them is clearly Oppenheimer. I don't know who the last person is. I think this was taken at one of the computers in Princeton or something. Yeah.
And the other question, the more serious question is, you said your quest is for a provable algorithm. And all these results involve probabilistic things which say that something works with very high probability. That's not quite the same thing as provable. So there's something that I'm not quite understanding.
Right. So by provable, I'm allowing randomized algorithms, which means algorithms that work with high probability. But now there's an important feature of this problem, which is that once you compute a putative approximate diagonalization of a matrix, you can check whether it's actually what you want. You can just compute the error, right? You can compute the backward error. And so if you want to turn an algorithm, a randomized algorithm that works almost all the time, into an algorithm that definitely works, you just repeat it until it works. And then it works with probability 1. But I mean, there's some tail behavior of the running time, yeah.